So in our last session, we have discussed about like the Young's modulus, rigidity modulus, bulk modulus, and all that. Then we had solved one more numerical on related to this pulley. Okay, what should be the minimum diameter in a pulley system? Okay, so let us solve some more numericals related to strength of material or that properties of mechanical properties of solids. Okay. So these are all some example problems from previous JE paper. Okay. So can you get me the specs? So two wires A and B are stretched by same load. Okay. If the area of cross section of wire A is double than that of B, then stress on B. Okay. So the question is like this. Okay. So two wires A and B. Okay. So let us say this is one wire. Okay. And then this is another wire. Okay. This I have put some weight here. I have put some weight here. This is fixed here. This is fixed here. This is wire A. And this is wire B. Okay. And this is wire A and this is wire B. Stress on B. Okay. So okay. So area of cross section of A. Okay. So area of cross section, let us say wire A. Okay. And this is area of cross section of wire B. Okay. So the area of cross section of wire A is double than that of wire B. Okay. So AA is equal to 2 times area of cross section of B. Okay. Then the stress on B, you compare the stress on B with stress on A. Okay. What is the relationship between sigma B and sigma A? Okay. This is very simple. Okay.
Yeah.
So you know sigma B is equal to a force on B divided by area of B, right? Sigma A is equal to force on A divided by area of A. Okay. So the load applied is same. Okay. So here you are applying W. Here you are also applying W.
Yeah.
So if that is the case, then this
Stress
will
of
become
B by
so
W.
FA is equal to FB is equal to your W, okay, which is equal to mg. Okay, you can write it as F. Okay.
Yeah.
So this your sigma B, it becomes F by area of cross section of B. Okay.
Yeah.
Sigma A becomes F by area of cross section of A. Okay. Now if you divide sigma A by sigma B, you just divide, this is equation 1, this is equation 2. Okay.
Yeah.
The sigma A by sigma B is equal to, so F by AA divided by F by AB, right?
Yeah.
So this become AB by AA. Okay. So
AA.
now we have told AB is half of AA. Okay. So just replace it by half of AA divided by AA. This becomes half. Okay. So if area of cross section is twice, then stress will be half. That is very simple. If area is 2 times, then stress will be half. That means you have a thick wire. Okay.
Yeah.
So thick wire means stress is less. Okay. So any structure also, if it is size is more, then stress will be less. So that is a very simple one.
Better.
now we'll go to the next one. Okay, which of the following statement related to stress strain relationship is correct? Okay, so there are several statements. So the statements are like this. Okay, so there are stress is linearly proportional to strain irrespective of magnitude of strain, which is not correct. Okay, so let us draw the stress strain diagram. Okay, so this is stress. Okay, in y-axis you have stress, in x-axis you have strain. Okay.
Yeah.
So I have told you that strain is nothing but your del L by L, and your stress is nothing but your force by area. Okay.
Yeah.
So the force you are changing, and the del L is changing, whereas A and L are not changing.
Yeah.
So this is your stress strain diagram. Let us say this is your a mild steel will again go to mild steel, and this is your stress strain diagram. The first statement is stress is linearly proportional to strain irrespective of magnitude of strain. So that means it is a wrong statement.
No.
Okay. So stress is, so this is your yield point. So beyond this is your proportional limit. So stress is proportional to strain only till proportional limit. So if the strain, so it is not that irrespective of strain. So in this region, so if the strain is very high, like the completely this region, okay,
Yeah.
completely this region, stress is not proportional to strain. Proportional means it is a straight line. Okay.
Yeah.
So beyond proportionality limit, it is not a straight line. Okay. So because this is a curve, so here what is the implication? Here you can see there is no change in stress.
Yeah.
With very little deformation,
Yeah.
with very little change in length, there is like that means here the stress is almost constant. That means after some time you don't have to apply any load to cause deformation. When it enters into plasticity, with very little application of load, it will start deforming. Okay,
Yeah.
that is called plasticity. So without applying further load, it will start deforming.
Yeah.
That means the strain will go on increasing.
Yeah.
Okay, so the statement that stress is proportional to strain irrespective of strain is not correct. Okay, then another statement made is, okay, stress is linearly proportional to strain above yield point. Incorrect, because this is your yield point. Okay, so beyond this, stress is not proportional to strain. If it is straight line, then only it is. Okay.
Yes.
Then the starts when stress is linearly proportional to strain for stress smaller than yield point. This statement is correct. So for a stress smaller than yield point, so this is my yield point. So a stress which is smaller than yield point is your proportional limit, which is otherwise called as your sigma y. Okay, and this stress is called your sigma. This is sigma p. This is sigma y, right?
Yeah.
So this sigma p is less than sigma y.
Yeah.
So till sigma p, like you can say yield stress, this you can say directly proportional to your proportionality stress, proportionality strain.
Yeah.
Okay, so they are proportional. So beyond proportional limit, they are not proportional.
Yeah.
Okay, so that statement is correct. Then there is some other statement. So stress strain curve is same for all materials. It's completely wrong. Okay, because this is for steel. Okay, this is for steel. Okay, for aluminium it is something different. Okay, it depends on what type of material it is. Okay,
Yeah.
so for aluminium it will be something like this. Okay, it will be something like this. So it may behave differently, and for steel this sigma y value is something around, let us say 700 MPa. Okay.
Yeah.
Whereas for aluminium, this value, this maximum value, it can be something around 500 MPa.
Yes, then
So it is because aluminium is less strong than steel. It is weaker than steel. Okay. So these are the cores for ductile material. So in ductile material, there will be lot of plastic deformation. Okay. So there will be lot of plastic deformation in ductile material. Okay. So these areas are all plasticity area. So ductile material, there will be lot of deformation. Whereas for brittle material, like there are some brittle material, let us say diamond. Diamond is very brittle.
Yeah.
Glass is very brittle. Similarly, in cast iron, very brittle. So the stress strain curve of those brittle material will be something like this. Okay, so this will be just, it will be a straight line.
After that,
After that, it will just break. That means there is hardly
No
any plastic
plastic
deformation. Okay, so you keep on increasing the load, at breaking point it will break. So the curve, this type of curve is not applicable for brittle material. Okay, so this is brittle material,
Yeah.
like diamond, glass, and all. So let us say glass. Okay, glass, you can see how a glass, if it drops, it breaks. You don't have to, beyond a point, you don't, it does not
Have
slowly
any
deform or anything. Okay. Okay. So it is not so. So stress is inversely proportional to strain. It is incorrect. Stress is always directly proportional to strain. It cannot be inversely proportional to strain. Okay. So now you understand that only one statement, that below any point,
it
stress
is
is directly
proportional.
proportional to strain. Okay. So now this is another question. So this type of question, the interpreting the stress strain diagram, what is brittle material, what is ductile material, all these understandings, based on this understanding and interpretations, there can be questions. Okay. Okay. There is another question. It's Young's modulus of a rigid body. Okay. So Young's modulus of rigid body.
Infinity.
So how it is infinity? Just will give one example. So let me say I have a rigid rod. Okay. So let us say this is rigid rod. Okay.
Yeah.
If it is rigid rod, whatever force you apply, okay, there won't be any deformation. So what if I show that this is the deformation? This deformation is equal to 0. It will not at all deform. Okay, that means it's completely rigid. So we know our Young's modulus Y is equal to stress by strain. Okay, so this is force per unit area divided by delta L. Okay, so this is delta L, right? This is your L, right? So this is delta L by L. So F by A, then this is 0. Okay, delta L by strain is equal to 0. If that is the case, it is infinite. So for rigid body, Young's modulus is infinite. Okay.
Yeah.
And the relationship between, there can be questions on the relationship between shear modulus and Young's modulus. Okay. So there can be this, you have to remember. Just you have to remember this rigidity modulus G is equal to E divided by 2 into 1 plus nu. Just this much you remember. Okay. So this new value is typically 0.3. Okay. Then rigidity modulus will be E into 2 plus 1, 2 into 1.3, which is equal to 2.6. Okay. So almost half of Young's modulus you can say, or little, or 1/3 of Young's modulus. Okay. So just remember this shear modulus is always less than Young's modulus. Okay. And some typical value of this Young's modulus, like say for steel, okay, E steel is equal to 210 GPa. Okay. 210 GPa. Okay.
10 power 11 in that range.
So 210 GPa means what? 210 into 10 to the power 9 Newton per meter square. Okay. Otherwise we can write it as 210 into 1000 MPa, right? So this is nothing but 210,000 MPa.
It's always in order of 10 power 11.
11, because it is 2.1 into 10 to the power 2 into 10 to the power 9. So it will be 2.1 into 10 to the power 11 Pascal. So that is the kind of value. So normally this we have two important value. One is sigma y steel, that yield point of steel. Okay, which is equal to, normally it will be 700 MPa. Okay. Yeah. Just remember, this is 700, this is 200, but this is MPa, this is GPa. Understood. So the Young's modulus value is almost 1000 times more than that of the
Stress.
yield strength. So normally for structural design, our stress what we are bothering about is the yield stress. So that is called the strength. Okay.
Yeah.
So sigma is called the strength, whereas E is more related to rigidity.
Material.
Like how like
The
infinitely
deformation.
rigid means it is infinite. So E is more related to rigidity,
Yeah.
whereas sigma is more related to your strength. Okay. So there are two things. One is strength, okay, and one is rigidity. Rigidity. So higher is the sigma y value, higher is its strength.
Yeah.
Okay, and higher is your E value, the more rigid it is. Okay. So E is equal to infinite means it's a completely ideal rigid body. Okay. So take a picture. No. So now you understand like Young's modulus of a rigid body. What does it mean? Okay. And relationship between rigidity modulus and Young's modulus. Okay. So the question is a liquid of bulk modulus K. Okay. So bulk modulus of a liquid modulus of a liquid is equal to K. Okay. And is compressed by applying an external pressure such that the density increase by 0.01%. Okay. So you have a liquid, you are applying pressure. Okay. You are applying pressure. Okay. Okay. So when you are applying pressure, okay, so the density, okay. So that when you are it's a compressible liquid, so the density increases by 0.01%. Okay. So the uh, density, let us say initially it was del 1 and finally it was del 2. So del 2 so delta del, okay, delta del, okay,
Yeah.
sorry, delta rho, okay. So delta rho is equal to 0.01 into rho, right?
Yeah.
That's how it will become.
Yeah.
So this delta rho is equal to 0.01 rho. So delta rho by delta is equal to 0.01. So you are compressing this liquid by pressure P, okay. So that delta del by rho, delta rho by rho is equal to 0.01.
Yeah.
0.01. So you know your bulk modulus is equal to pressure divided by delta V by V, right? This is the equation, okay. So this delta rho by rho, otherwise you can write it as delta rho is what? Mass per
by
unit
volume.
volume. So m by delta V divided by m by V is equal to 0.01, right?
Yeah.
So that means your
Mass cancel.
mass cancel. So it is become V by delta V, right?
Is equal to 0.01.
Is equal to 0.01.
For reciprocal of that is 1 by 0.0.
The reciprocal of delta V by V is equal to 1 by 0.01, which is 1 by 1 by 100, okay, which is equal to 100, right?
Yeah.
So K is equal to pressure divided by 100.
Yeah.
Right? Sure. Right?
Yeah.
So Is there anything wrong with this? So let us say P by K is equal to V by delta V, right?
Yeah.
P by K is equal to V by delta V. Okay. So V
which is equal to 0.01.
V by delta V is equal to 0.01.
Yeah.
Okay. If that is the case, then it will be 0.01, right?
Yeah.
But, okay, so that's the answer. Okay, so then we'll do some more. Okay. Okay, so the one related to rock or compressive strength will do.
Okay.
So the height of a mountain is h. The density of rock is okay. So we have a mountain. Okay, let us say we have a mountain. Okay, so we have a mountain. Let us say like this. So we have to find out the mountain. So and mountain has rock whose density is 3000 kg per meter cube. So this mountain has rocks. Okay, so rocks. Uh, okay, so these are the rocks whose density is 3000 kg per meter cube.
Yeah.
This is density of rock is 3000 kg per meter cube, and the elastic limit of rock is 3 into 10 to the power 8 MPa. Okay, so the elastic limit, you can say that strength. Okay, this is not Young's model, the strength.
Okay.
So the strength we can say ultimate or whatever you write. Okay, is equal to 3 into 10 to the power 8, 3 into 10 to the power 8 Newton per meter square. Okay, so you can otherwise call it as 300 MPa or whatever.
Yeah.
Okay, so this is the this is your strength, the elastic limit.
Yeah.
If you draw for rock, it will be something like this. So maybe the rocks are like, if it is brittle, we can say that this value is your 300 MPa, right?
Yeah. After that it will break.
After that it will break. So this stress, this sigma, you can say it is a ultimate tensile or ultimate compressive stress here. Okay.
Yeah.
So there are two types of test. Okay. So this is tensile. Okay. And when you check in this direction, this is called compressive. We see the rocks are good at taking compressive loads. Okay.
Yeah.
So even in our structural material like concretes, they are carrying the compressive load.
Yeah.
How they are carrying? Because in your house you have different walls. Okay.
Yeah.
You have different walls. Okay. So these walls are made of cement and concrete. Okay.
Yeah.
So on this wall you will have your all your slabs and so in your building design you will have the roof. Okay.
Yeah.
So these vertical members will be called as the columns. Okay. These vertical members will be called as the column. Also in your house, this transverse member will be called as the beams. Okay.
Yeah.
So from the roof, the load will get transferred to your beams. Okay.
Yeah.
So the load will get transferred to your the beams. The
Yeah.
horizontal members are beams. and the beam will transfer the load to the columns. Okay, so if you see this is your building, so there will be this kind of column beams. Okay, so like this you have beams.
Yeah.
So and here you will have you will have the roof, and these are the beams. Okay,
Yeah.
these are your beams, and there will be some vertical members like this, which are your columns, right? The vertical members are your columns.
Yeah.
So actually, how do you design a building? You will have different types of load. You will have live load and you will have dead load. Okay.
Yeah.
So the live loads are kind of like the structural weight which will always be there. That will be your dead load. Okay. So so these beams, the weight of the roof and everything,
Yeah.
and the weight of the beams will finally get transferred to the ground through these columns. So these columns will be subjected to, finally if you draw the free body diagram of this column,
Yeah.
they will be subjected to a compressive load.
From the beams.
From the beam and the roof,
Yeah.
it will be subjected to compressive load. So these beams are made of concretes. Okay.
Yeah.
This beam, if you take a cross section of this beam, if it is a rectangular cross section, it will be made of concretes. Okay, it will be made of concretes, and in between concretes you will have steel rods.
Yeah.
Okay, so in between concrete you will have circular rods. Okay, so for building construction, in addition to concrete, they use steel rods, because that will improve its load carrying capability. That's why this is called reinforced concrete. Okay, so in beams you are using reinforced concrete. So this is your concrete, whereas this is your steel. So if you don't have steel, then your size of your wall will be more. So if you put more steel, it can, for a lesser cross-sectional area, it can take more load. So that's why it is called reinforced concrete structure, RCC. Okay, so RCC, R stands for reinforced, C means reinforced concrete. Okay, so most of the buildings, the columns are reinforced concrete.
With steel and concrete.
Yeah. So here it is being given as, like, say, here. Okay, so they are asking, we started from the mountain, so let us say the height of the mountain is h. Okay, so the height of the mountain is h. So the question is, the height of the mountain, density of rock is given, if the elastic modulus. Okay, find the height of the mountain. Okay. Okay, so let us say the density of the rock is rho. Okay, this is rho. Okay, right? And if you take a cross-sectional area of this mountain, let it be, say, A. Okay, get the cross-sectional area the A. Okay, then we can find out the stress to be the stress is equal to the force by area. Okay. So what is the force on the lowermost thing?
Ground.
So lowermost concrete layer, that will be the weight of the mountain. Okay. Weight of the mountain divided by area of cross section of the mountain. So what is the weight of the mountain?
mg.
Weight is equal to m into g. Okay.
Yeah.
And this m is nothing but your rho into v into g. Okay.
Yeah.
So that is the weight. And okay, so and again rho into v into g. Okay, and then this rho you can write as a into h, because volume is nothing but cross sectional area into height. Okay, into g.
Yeah.
Right. So your weight is equal to rho into A into H into G.
Then area will cancel.
So your stress will be
Rho G.
Your stress will be rho A H into G.
By A.
That divided by your A, which is equal to, you can put 3 into 10 to the power 8.
Rho G H is.
That is the strength. So what you are getting here is stress. Okay. So stress should not exceed strength.
3 into 10.
So this is your strength of concrete.
Maximum stress.
So this strength is property of the rock, whereas stress is what you are getting.
Okay, I understand.
So your rho A H into G divided by A is equal to 3 into 10 power 8 Newton per meter square. So now your A cancels, and density of rock, you know it, 3000 kg per meter cube. You know G is equal to 10 meter per second square.
3 into 10 power 3 into 10. So 3 into 10 power 4 into H is equal to 10 power 8.
So it will be
10 power 4 by 10
this
power
will be rho is equal to 3 into 10 to power 3, right?
Yeah.
Okay. Then H we do not know.
Into 10.
G is 10, right?
So
is equal to
10 power
3 into 10 to
power
power 8. Okay.
3 cancel.
So H is equal to 10 to power 8 divided by 10 to power 4. That means it is 10 to power 4 meter. Right? So 10,000 meter.
Yeah.
Okay, so
This is easy.
so you can understand.
Yeah.
Okay.
Wait.
Okay, so there is another question, like the ratio of hydraulic stress to corresponding strain is, okay. So hydraulic stress, okay. So normally we will have some hydraulic press and all, you have studied in our fluid mechanics. So it will have some piston cylinder kind of arrangement, okay. So let us say this is my piston, okay. So I have some, let us say I have some water inside it or some hydraulic fluid, okay. There will be some hydraulic oil or whatever, okay. So I am pressurizing it. So they are asking the ratio of hydraulic stress to corresponding strain. So I know that is nothing but your bulk modulus. So P divided by volumetric strain, okay. So this volumetric strain is the corresponding strain, and I am applying pressure. So this ratio is nothing but your bulk modulus. So when you are compressing some fluid, compressible fluid, the bulk modulus is important. When it is solid, the Young's modulus or rigidity modulus. But when it is compressible fluid like hydraulic oil or whatever, it will be
bulk modulus.
This hydraulic oil, it will generate a pressurized oil. So this pressurized oil normally in aircraft and all, it will be used, this pressure will be used to actuate different control surfaces. Okay, so in aircraft you will have flaps, when you travel, you can see in the wing, in the leading edge, on the front side you will have some slats, in the rear side you will have some flaps, and also those will, during landing and takeoff, those will come down or go up and all. So that those things are actuated by these hydraulic oils. Okay. Anyway, we will not go into details of that. Okay, so one more numerical we can do. A crane. Okay. So a crane with a steel cable of length 11 mm and radius 2 cm. Okay. So I have a cable. I have a cable of length 11 mm. So length is 11 meter. Okay. The length of the cable is 11 meter. Radius is 2 centimeter. So if we take a cross section, okay, so this radius, so let us say this R, okay, so this R value is 2 centimeter. Okay, so this is R, and employed to lift a block of concrete mass of 40 tons. Okay, so this I am putting a mass of, let us say, 40 tons. Okay, here
Okay.
40 tons. This is the let us say this is the force that is being applied. Okay, so 40 tons. Okay, Young's modulus of steel is 2 into 10 to the power 11 Pascal. Okay. So let us say this is made of steel. Okay. Okay.
Yeah.
And its Young's modulus is equal to 2 into 10 to the power 11 Pascal. Okay. So which is nothing but 2 into 10 to the power 11 Newton per meter square.
Yeah.
Okay. So now they are saying what will roughly the increasing length of cable because of the lifting block. Okay. So this can be easily solved. This is a direct one.
Yeah.
Okay. So Young's modulus, you know. So your Y value is nothing but your force by so stress by strain. Okay. So this is nothing but your
del L by
this is nothing but your stress divided by strain. So this stress is nothing but your force by area, and this strain is nothing but your delta L by L. Okay.
Yeah.
So here you know your Young's modulus, which is 2 into 10 to the power 11. Okay.
Force
Then
is 40 ton into inch.
Then force. So force is 40 tons. Here this is important as far as unit conversion is concerned.
Into G.
So 1 ton is nothing but your 10 to the power 3 kg.
Yeah.
Right?
Yeah.
40 tons means 1 ton is 1000 kg. 1 quintal is 100 kg. So 40 tons, this is force. Force we have to multiply by acceleration due to gravity. So you multiply it by
4
G.
into 10
so it will
power
become
5.
40 into 10 to the power 4 Newton, or
4
it will
into
become
10
4
power
into 10 to the power 5 Newton.
Yeah.
Okay. So this is your force. Okay.
Yeah.
Then so now what they are asking?
Del L.
Del L. Okay. So we know the diameter is 2 centimeter. Okay. So this I can area cross section will be, let us say, pi r square, right? So pi r square. So pi into centimeter I can convert into meter. Okay, because everything is in meter, right? So 10 to the power minus 2 whole square. So I know area, I know force, I know the length as 11 meter. Everything is meter. L as
11 meter.
11 meter. So my 2 into 10 to the power 11 is equal to, force is equal to 4 into 10 to the power 5
into 11
divided by area of cross section is pi
into
into 4
into
into 10 to the power minus 4. Okay, so this is force by area. Then delta L I do not know. Length I know as 11 meter. So by knowing all this, I can find out what is delta L. Okay, so this is easy. Okay. Okay, so that's all. We have covered some 8 to 10 numericals on this thing. Okay. Thank you.